Hello and welcome to another instructional video from CoreTigo. During this video, I will be showing how to map process data inside a Studio 5000 program. In this video, I will be using one Compact Logix PLC, one TigoMaster 2TH, and a TigoBridge A2 connected to an IO-Link distance sensor. I will also be using a second TigoBridge A2 connected to a TigoConverter C1, which is connected to an analog distance sensor. Then I will be showing how to map the process data from both of these inputs. Before going into examples, I will take a few minutes to explain the process data layout. The layout can be found in the TigoMaster 2TH's user manual, which is listed on CoreTigo's customer portal under Download Center, IO-Link Wireless Masters, TigoMaster 2TH, or by simply searching for Ethernet and selecting the first link. Inside the user manual, navigate to Process Data Mapping, listed on page 90. Here you can see that there are 10 different types of connections available. There are two main types of connections, those for 8 wireless ports and those for 16 wireless ports. For both types of connections, there are options for process data control or monitoring. During this video, I will be using the second connection, which will allow me to communicate and/or control 32 bytes of process data on 8 wireless ports. And please note that if users select the first connection, the PLC will configure the wireless ports, and thus will overwrite any configurations completed in Tigo Engine. Inside the data mapping, we see that the first 4 bytes are either padding bytes or reserved for future expansion. After the first 4 bytes, the process data of the devices begins. The 5th byte begins with a flag byte indicating the statuses of the wireless and wired IO-Link ports. Inside this status byte, bit 3 indicates if there is a wireless or wired IO-Link event, e.g. under voltage, over temperature, etc. Bit 5 indicates if the wireless port is connected to a wireless device, and bit 7 indicates if the wired IO-Link process input data is valid. These flags are available on each wireless port. After the status byte, also called the PQI byte, there is a byte of padding zeros. Then the process data for the wireless port begins. The length of the process data section depends on the type of Ethernet connection selected when making your module inside the PLC. This pattern of PQI bytes, padding byte, and process data bytes repeats for all wireless ports. The process data output is symmetric to the process data input. The only difference is that the status byte available on the input side is an enable byte on the output side. This byte needs to be set to a non-zero value in order to control the process data outputs for the wireless port. During the next portion of this video, I will go over some examples inside Studio 5000. First, I'll register the TigoMaster's EDS file by navigating to Tools and selecting EDS Hardware Installation Tool. Then I select the EDS file I downloaded from the customer portal and unzipped. I next select the standard EDS file without ZipSync and click through the steps presented in the wizard. Next, I create a TigoMaster module underneath the Ethernet tree of my PLC. Then I name the TigoMaster, give it an IP address, and select the connection type by clicking Change. As discussed earlier, there are 10 types of connections. During this video, I will not use the first connection, as it will require that I configure the TigoMaster via the PLC. However, I will use the second connection type, which will allow me to communicate 32 bytes of information to 8 wireless ports. Once the connection is selected and the module is created, the tags will be automatically created as well. Already, I have everything I need to begin reading inputs and controlling outputs. However, there is an optional step that I will be completing. CoreTigo has created a tag description file which will provide comments to every byte and bit of a TigoMaster's tags. This file is located on the customer portal under the knowledge base. It can be found by going to CoreTigo's customer portal and searching for tag description. Open the article and scroll to the bottom to download the tag description CSV. Save the CSV to your PC, then open the CSV, which corresponds to the connection type selected when creating your module. I selected the second connection, so I will open the CSV comment list connections 1 through 4. Once inside the CSV, I will find and replace all instances of place your module's name here with the name of my module. So in this case, I will replace it with TigoMaster 2th. Then I'll hit replace, and then I'll save the CSV file. Back inside my Logix program, I will select Tools, Import, Tag and Logic Comments. Then I'll select the file I just edited. Instantly, the tag comments are added, and I can clearly see the data layout discussed earlier in this video. In our first example, we will read the inputs from an IO-Link distance sensor. The distance sensor has 16 bits of resolution and will be paired to wireless port 1. The tags generated for the TigoMaster are 1 byte long. Therefore, I will load 2 of these bytes into a single variable which is 2 bytes long. To do this, I will use Rockwell's pre-built BTD block. I will add the block to my logic, then select the correct byte from my TigoMaster's tags. In my case, the first byte of wireless port 1 contains my first byte of data. I'll select that byte as my source byte, then set the source bit to 0, and then create a new DINT tag named distance to receive this data. I set the destination bit as 0, and the length of the transfer will be 8 bits. Then I will repeat this process for the second byte of data. I set the source bit as 0, set the destination as the tag distance that we just created, and change the destination bit to 8. The length of this transfer remains the same, 8 bits. The data conditioning of my 16-bit distance value is now complete, and once I go online, I can see that a distance of about 5 centimeters is correctly translated to a value of roughly 5,000. Luckily, the IO-Link distance sensor we used in example 1 can also be used as an analog device. In example 2, we will use the distance sensor as an analog device. We will do this by using a Tigo converter connected to the analog pin of the distance sensor. Then the Tigo converter will connect to a Tigo bridge A2. Inside the Studio 5000 program, I will load the 2 bytes of process data from my analog distance sensor into a single tag. Just as before, I used the BTD blocks. However, from the tag list, I can see that the first 2 bytes of process data does not include the distance reading from the analog device. Therefore, bytes 3 and 4 of the process data on wireless port 2 will be used. Please note that the Tigo converter loads the most significant bytes of data first, followed by the least significant bytes of data. This is the opposite order of how Rockwell does it. So when you do your BTD transfers, you'll start with your 4th byte of data, and then you'll follow it up with your 3rd byte of data. When I first connected the distance sensor, I taught the minimum and maximum distance on the sensor as 20 centimeters and 50 centimeters respectively. I will use those values inside Rockwell's SCL block. The SCL block scales analog inputs into readable values. The SCL block can only be used in a function block diagram. I'll add a function block diagram routine. I'll edit the routine and add an SCL block. Then I'll add an input element and place the tag analog distance into the input element. Then I will create an output element and create a new tag called analog scaled and make it a floating type of variable. Then inside the SCL block, I set the in raw max as 20,000 for 20 milliamps and the in raw min as 4,000 for 4 milliamps. I will then set the EU max as 50 and the EU min as 20 for 50 and 20 centimeters respectively. Back in the main routine, I will add a new run, and then I will add a jump to subroutine command, and call the scaling function that I created, and then I'll finalize my edits. Once my edits are finalized, I'll be able to read the value called analog scaled. And here I can see that the distance sensor accurately reads a distance of about 22 centimeters. This completes our video explaining how to map I/O data from your wireless master into your Rockwell PLC. If you have any more questions, please email us at support@CoreTigo.com, and if you would like general information about IO-Link Wireless, please email us at info@CoreTigo.com or visit our website. Thank you.